right, so good morning. Let's start. So last time we were looking or started looking at examples of symplectic manifolds, and now maybe I want to cover one more big class of examples. So let's say examples symplectic manifolds, and we had, I think, 3 classes, and that will be the class number 4. So I think probably many of you, maybe all of you, already heard about them. So this is an interaction between symplectic and complex geometry, and they go under the name of Keller manifolds. So let me start with the following consideration. Let's say N is now a complex manifold. So up to now we were always looking at manifolds over R, but now let's look at a manifold over C. And so let's consider, well, the tangent bundle to N, I just temporarily denoted TCN just to stress that this is a bundle of complex vector spaces. So complex tangent bundle. And we would like to have on this complex tangent bundle, let's say at a point M or point N, we would like to have a Hermitian structure. Hermitian structure, which nicely, smoothly depends on the point. So we want fiber-wise Hermitian products on those complex vector spaces. Maybe like the first question, what do you think? Is it always possible to have such a Hermitian structure, or would there be some difficulties with it? So I about to say let's choose a Hermitian structure, but maybe they don't exist, or how is it? What?
Well, if it's just smooth, you can use the same argument for Riemannian metrics.
Yeah, exactly. You can just glue by partition of unity. Exactly. So those H's. Sorry? So they exist by gluing with partition of 1. So if you have charts, so you have an atlas, UI, and in each chart you can, of course, define HI, Hermitian structure. Then you can define a sum of HI times, I'm not sure what is your preferred notation for partition of unity. Is it chi or eta or whatever it is, let's say chi I, for chi's being the partition of unity. Right, so those H's exist. Now what we can do, remember we already had in linear algebra a relation between Hermitian structures and 2 forms. So what we can say, we can now declare that M is equal to N, let me know, denote it this way, and R, and here I just mean by that we consider N as a manifold over R, right? All the charts, instead of thinking of them as Cn, we think of them as R to n, and all the maps, forget that they're holomorphic maps, they're just smooth maps. So in this way, we obtain a structure of a real manifold on M. And now we simply play the same trick as before. So we take two tangent vectors, and we declare omega m of uv to be the imaginary part of h m of uv. Right. So this assignment defines omega, which is a two-form on M. And we know from linear algebra it is automatic that the kernel of omega M is 0 for all M. Right? So this is now automatic, because whenever you have this Hermitian product and you construct a two-form from the Hermitian product, the kernel is automatically 0. Right. Or we can put it in this way, omega is non-degenerate. Now, here is the definition. We say that the pair NH is Keller if the corresponding omega is closed. Right? So this is a kind of integrability condition, or this is a kind of differential equation that we impose on omega. That is, we impose it on H in some way, right? Of course, this implies that M omega is symplectic. Right? So this is one more source of symplectic manifolds, and let me give you a couple of examples. I think later on we probably have more examples, considerably more examples of this thought, but now maybe just some very, very simple cases and also some elementary statements about Keller manifolds. So one example is, of course, if you choose n to be simply Cn, and we choose H to be a constant Hermitian form. Here, well, of course, Tcn will be identified with just equal to Cn again. And we can say that H of uv is simply the standard Hermitian form with our slightly weird physics-like notations, right? That's the first one, which is complex conjugate, and the second one, which has no conjugation, right? So that's the standard Hermitian structure. Maybe one more remark. So just in writing, we can probably, I don't know, what would you say? So I would abbreviate this writing in the following way. I would say that H is sum of dZi's absolute value squares, right? So that's one way to encode it. Maybe a small exercise. Check that the corresponding omega is up to a multiple, maybe 1/2, I'm not quite sure, coincides with omega 0, the standard symplectic structure on R to n for the following choice of coordinates. So we can encode zi's as qi's plus I pi's, where q's and p's, they will be future canonical coordinates. And then here up to some multiple, we'll obtain omega obtained from this construction equal to the standard symplectic form. Now let me look at a slightly more involved example. So let me choose n to be equal to CP1. So these are, recall the classes of pairs of complex numbers. They are not allowed to be both equal to 0 at the same time. And so we consider equivalence under multiplying by non-vanishing complex numbers of both elements. Right? So now we need to define this Hermitian form H, and let me do it in the following way. I'm not sure, again, whether it's optimal or not. So let me recall that GL to C, so these are invariable 2x2 matrices, that they act on CP1 simply in the following way. So if we take a matrix, and let me write components Z1 and Z2 in this way. So this is just, oops, sorry. So this is just an action so the standard action on the two-dimensional complex vectors, and then this action descends to the action on classes. Right? So let me do the following. By the way, I don't know, notation, is it fine for everybody? So let me recall that inside GL to C, we have a subgroup U2 of unitary 2x2 matrices. So let's say G in GL to C, and here G star is equal to G minus 1, where this is a Hermitian conjugation, and this is just the inverse. So unitary matrices. And it is easy to check that, okay, maybe even one more thing. So there is a subgroup SU2 of unitary matrices of determinant equal to 1. Now, it's easy to check that the action of this subgroup of CP1 is transitive. In fact, can you tell me how should I imagine it geometrically? Probably, like, I just want to know whether you how easy it is for you. Is it like all trivial, or like do you how do you imagine this? What's the picture you have in mind if I tell you there is this SU2 acting on CP1? How does it look like?
Mobius oscillation.
Okay. Good answer. Some other answers?
For CP1 is a sphere. And
That's right. That I want. Okay, that's what I want to refer to. So the picture that I want you to have, or like one possible picture. Of course, there are many possible pictures, but one picture that I want you to have, and we're going to see it in more detail later, but still, so CP1 is a two-sphere, right? Especially if we think about it as a real manifold. So CP1, so this is the two-sphere. Now this SU2, how does it act on a two-sphere?
Rotation.
Right, exactly. It acts by rotations. So SU2 acts by rotations of this two-sphere. Of course, rotations do act transitively on the two-sphere. Of course, here in this picture, one would need to check that this is indeed the case, that, say, in a moment we go to a chart and we'll see Möbius transformations, and of course one would need to check that SU2 is good enough to reach all the points, including infinity. Right. Okay. So now my plan. So my plan is as follows. So indeed, choose a chart. Right, so there will be points of this form, Z1. So let's say it's U inside CP1. And now in this chart, this action will look as follows. So now A, B, C, D will be sending Z to the ratio of the two, right? If we normalize the second one to be 1, then the first one will become a ratio of the first by the second. Right. And I suggest to do the following. Fix H on the tangent space at the point 0, 1, right? So we have a point 0, 1 somewhere on our sphere. So here there is a tangent space there, and we just want to fix H there. And let's fix H to be simply the absolute value of dz squared, right? And then define H on all of CP1 by SU2 invariance, right? So let's require the following. So if we want to go to some other point, so here there would be a tangent space. So let's require that if you rotate this point to that point, that the H here will be the image of H there. Just a test question for you. Is it automatic that it works? So I'm telling you, let's define H to be a Hermitian structure, hopefully unique Hermitian structure on CP1, which is SU2 invariant and which coincides at the point 0, 1 with this guy, right? That's what I'm telling you in a more kind of explicit language. So is it obvious whether it's gonna that it's gonna work.
Well, at least it should be really invariant around the subgroup that exists at time.
Right. I'll consider whether you should be forbidden to make comments. No, it's very good. Yeah, of course. Like I think that's right. That was the kind of what I was asking about, right? So in fact, if the action were free and transitive, right, then it would have been automatic. So imagine that there is no subgroup which stabilizes the point, right? So okay, that's not the case here, but it may be the case in other situations. Then you take your object in one point and you bring it to all other points by your group action. So the object that you bring there, it will be automatically invariant. And of course, it will be automatically unique because you bring it by a unique transformation to that point, and then, well, there it is. Now the problem is that there might be different elements which bring you here. The question is, do you get the same? Or maybe put differently, so there are some elements which preserve the point. So I rotate the sphere, right? Say around the nose pole, and the nose pole stays the same. So we need to check. We need to check that H01 preserved by the stabilizer subgroup of 0,1. Now, what's the stabilizer subgroup of 0,1? So this will be all SU2 transformations, all unitary matrices which map 0 to 0. Well, in order to map 0 to 0, you need to have B equal to 0, right? So, so this stabilizer of the point 0, 1, it consists of matrices A, B, C, D equal to G. So G is in SU2, and it is clear that B has to be equal to 0. But you know, for 2 by 2 unitary matrices, if B is equal to 0, then C is also equal to 0, right? And then so it's actually diagonal. And since it's unitary and determinant is equal to 1, we have AD equal to 1, and the absolute value of any of them is also equal to 1, right? So in fact, so that's this subgroup, exponential I phi, exponential minus I phi, 0, 0. So that's the stabilizer group. Now, the question is whether this guy is invariant under the action of that group. And let me leave it as an exercise. So it's easy to check that indeed if you act on disease by these elements, one needs to compute, one needs to differentiate the left-hand side and the right-hand side and see what's the action on disease. But if one checks it, then one sees that such elements map dz squared to itself. So this means that actually this H exists, and it defines a Hermitian structure, an SU2 invariant Hermitian structure on CP1. Now the question is whether it's going to be a Keller manifold with this Hermitian structure. So let's define omega as the imaginary part of H, as we did before. And now the question is, what is d omega? Now here, what is d omega? Sorry for asking somewhat trivial questions. Is it going to be like difficult or easy, or how is it? What?
It's 0 because the imaginary part of H is 0. Wait.
No, but you know, this is a notational. You see, this is a notational problem. The imaginary part is not equal to 0. I just tried it that way. Remember, that's the Hermitian, that's just the standard Hermitian structure on this one-dimensional vector space. No, the imaginary part is not going to be 0, but still, the omega might be 0, right? We know actually that omega is non-degenerate. Whenever you... Yeah, exactly. So for dimensional reasons, remember, we had this point 2. If we have a non-degenerate 2 form on the surface, a volume form, so then it's automatically symplectic because there is this d omega has nowhere to live, right? So because this is in omega 3 of CP1 viewed as a real manifold, and this is 0 because there is no like 3 forms. Just for dimensional reasons. So in this way, we obtain an SU2 invariant symplectic structure on CP1. And well, here you see we did it in a somewhat painful way. Later on, we'll have a lot more kind of fluid and industrial ways to produce such symplectic structures. Here, I just wanted to show you once that, okay, one can try to manufacture it, and it works, of course, with some pain, but so one important remark, or maybe just before we go into a remark, so we looked at cotangent bundles, and we are now looking at Keller manifolds. And these are examples of very nice symplectic manifolds. So here, in principle, it should be easy for us to work with them. So maybe at the moment it's not that easy, but later on that should be our friends in the symplectic world. If we want to test something, we typically go to cotangent bundles or Keller manifolds. So one good property of Keller manifolds. Suppose that NH is Keller, and suppose that I'm not sure. I need another letter. Let's say S. It's inside N. Is a complex submanifold of N. So then S together with H restricted to the tangent bundle to S is again Keller. So why is that? So basically, there are two observations which are both very easy. So the first observation is, of course, for any point S of S, the tangent space in S at this point is a complex subspace of the tangent space in the big manifold. And so H, Hermitian structure on TSN, restricts to a Hermitian structure on the subspace, right? Because this is what? This is just the Hermitian product. All the properties of the Hermitian product, they will automatically be satisfied for a subspace. So So this seems to be okay. Now, what about omega s and omega n? So let me denote by I the embedding of S into N. Right? S is a submanifold, so I can think of it as being embedded by some map. So this map is just tautologically maps the point, any point of S to itself. So here we have let me put it this way, the 2 form, which is the imaginary part of Hn, and here we have the 2 form, which is the imaginary part of Hs. And so Hn restricted to Ts is Hs, omega n restricted to the tangent space TSS is omega s. Right? So this is just by construction, right? You have these 2 simple steps. You produce 2 forms from Hermitian forms. And here, since one is restricted, the other one is also restricted. But this means a very, very nice thing, that d omega s is d of this iota star omega n. And this means that this is iota star of d omega n, and this means this is 0. So you just automatically get this differential equation. So kind of even I'm trying to write it kind of to make it long, right? But in principle, the argument is very, very short. So actually, later on, we'll compare it to the situation with symplectic manifolds. The situation with Keller manifolds, from this perspective, is very, very nice. Basically, you take any complex submanifold, and you get a new Keller manifold, which is very, very beautiful. All right. Now, let me introduce one of the most important tools in elementary symplectic geometry. It goes under the name of Moser lemma or Moser trick. So we're going to use it many times today and later on. And so there are various formulations of the Moser lemma. And I'll choose a kind of rather honest and maybe not a very beautiful formulation. But then we'll see how it's adapted to various situations. So let me put it in the following way. So M will be a manifold, and omega t will be a smooth family of symplectic forms. So here T is a real parameter. Perhaps it takes values in some segment of R, perhaps in the whole of R. So I have a smooth family of symplectic structures, so many of them on M. So now, in fact, you see, I even don't want to state it as a proposition. Let me develop a little bit this structure. So there will be 2 assumptions. First of all, assume that the derivative of this family consists of exact forms, and actually we know the primitives. So the left-hand side is exact, and for the right-hand side we have some alpha t, a family, a smooth family of one forms. Such that the Theorem differentials of alpha t reproduce d omega t over dt. Of course, this assumption implies that the cohomology class of omega t is constant. So it is not, it's independent of t. So then we can do the following. We can define a smooth family of vector fields such that for some reason one needs to change a sign, such that the contractions with the corresponding two forms give those primitives alpha t. Of course, we know that in fact Vt is pi t sharp, right? The inverse bivector computed on alpha t and with a minus sign.
Maybe it's a stupid question, but how do you define the omega t in t?
Well, I assume that this is right. So I have a smooth family in each. What's kind of what would be the problem? Just by the ordinary formula for the derivative.
Oh, okay.
Right. So I have a family omega t. I take, as we are taught in a calculus class, omega of t plus epsilon minus omega of t divided by epsilon and take a limit. So I think here there is no, I kind of in some points I'm cheating. Here I don't think I'm cheating too much. But it's good. You should be able to catch me on some occasions. Right. So we define this family of vector fields, and now assume so Vt integrates to, let's say, phi t the family of diffeomorphisms of M with phi 0 equal to identity. So I want to integrate this family of vector fields to a family of diffeomorphisms. In fact, in general, this is not guaranteed to work. Or for sure, it's not guaranteed to work for all t. So we'll have to think about it every time. But now I just assume that this integration works. So then the conclusion of the Moser lemma is that phi t star omega t is equal to omega 0. Right. So sometimes the Moser lemma is formulated not completely accurately in the following way, that if you have two symplectic forms in the same cohomology class, then the manifolds endowed with these two forms are symplectomorphic. As you see, at least kind of if you want to do it accurately, there is a little bit of assumptions on the way. So this is not a very serious assumption if you assume this. So then more or less if the class of omega t is constant, then you can produce, well, in more or less all the situations, a smooth family of primitives. Now, this is, of course, a big assumption. So Vt, depending on the situation, may integrate or may not integrate or whatever. So let me finish this hour with a very short and elementary proof of the Moser lemma. Right. So let's consider the derivative of phi t star omega t with respect to t. So then, if omega t were a constant, if it didn't depend on t, then we actually, last time we wrote already formulas for such derivatives. So then we've got this guy. So phi t star, and here the Lie derivative with vt, because phi t integrates vt, right? So that would be then vt of omega t. So this would have been a correct formula if there were no t-dependence of omega. But now t-dependence of omega is very easy to take into account, right? After all, we're just using the Leibniz rule. We're differentiating phi. That's the differentiation of phi. And the derivative of omega is simply the derivative of omega. Right. So, now we get phi t star, and here L of vt omega t plus d omega t over dt. And you notice again, right, since the proof is so short, I'm trying to make it long. But it resists, right? It anyways wants to end. So, right, so this is phi t star. Now what about this guy? Here I think we need to use the Curtin's magic formula, as usual, omega t. And d omega over dt is this guy, d alpha t. Now, the family omega t consists of symplectic forms. Therefore, this term vanishes, right? Because d omega t is 0. Now, this term, actually we defined vt such that iota vt of omega t is minus alpha t, right? So this gives us minus d alpha t, and that's from the definition of the Moser vector field, right? So that this comes from iota of vt omega t equal minus alpha t. So all in all, we get minus d alpha t plus d alpha t, which safely gives us 0. You see, that's the whole proof. I succeeded in making it into 3 lines, even though 1 line is like... So maybe just the last comment. I already said the words. So here vt is called the Moser vector field. Maybe one more remark again before we erase everything. So, like one particular situation when this assumption comes more or less for free, right? So the integration assumption. So I think it's okay if M is compact. So then there is no problem with integration. That's what we're gonna often use. And here again, like I wrote it in one direction. I'm just looking for some more visible color. But So if omega t is in the same cohomology class independently of t, then usually you can produce a smooth family of primitives. So this is usually fine. So this is often not fine, but with some work, maybe one can make it fine. Right. So this is one of, as you see, this is a very easy result, but this is one of the central results in symplectic geometry. We're going to use it just after the break to prove various things. And well, let's have a break. Well, let's continue. So as I said, this Ulema is a very, very useful tool. It seems to be a simple tool, but it's very useful. And now we're going to explore some applications of the Ulema. So the first one, famously, is the Darboux theorem. Let me Darboux theorem. Right. So we start with m omega symplectic. We choose a point of m, and of course we know that the tangent space at this point, together with the value of the two form, is a symplectic vector space. Well, it's a symplectic vector space, but this means that we can think of it as a symplectic manifold with a constant two form. Right? So it's a symplectic vector space, but this means that it's also this constant two form omega m. So now we just, instead of kind of these are just two different viewpoints on the same object. Right? So now here is the statement. So then there is a neighborhood, let's say U, of our point in M, and a neighborhood V of the origin in TMM. Right. And let's say phi. Here, the kind of direction of the map, maybe we'll have to negotiate later on. And the symplectomorphism phi from V endowed with the constant symplectic form omega m to U endowed with the symplectic form omega. It's a symplectomorphism such that phi of 0 is equal to m, and the derivative of phi at 0 is the identity of the tangent space. Right. So this is a simple but very, very strong result in symplectic geometry. It basically tells us the following, right? So near any point M, I can choose a chart which can be identified with an open subset of symplectic vector space together with a constant symplectic structure. So let me recall, so there is a corollary of this theorem. So let me recall that we already proved that the symplectic vector space together with a constant symplectic form is always symplectomorphic to the vector space R to N together with the standard symplectic structure, the sum of dqi's with dpi's. So this was a highlight of our linear algebra story. Right? So in fact, so this chart with this symplectic structure omega m, which is constant, we can think of it as just the standard chart of this symplectic form, which is just of that dqi wedge dpi form. So such charts are called Darboux charts. And now the theorem says that in the neighborhood of every point we can define a Darboux chart, and this means that eventually we can cover our symplectic manifold with Darboux charts. Right? So there will be kind of Darboux charts of this form, and then the transformations between them will be symplectomorphisms between the standard symplectic structure and itself. So, so this kind of gives you a way, maybe that's not the most efficient way to study symplectic manifolds, especially not for our problems which are related to group actions later on in the course, but it gives you a very, very, very strong indication on how symplectic manifolds locally look like. So another thing, maybe somewhat informally, says that symplectic manifolds have no local invariance. Right? So a neighborhood of every point in a symplectic manifold, it always looks the same. Right? You can always identify it with neighborhood of the origin in R to N with this standard symplectic form. So this is in sharp contrast with other geometries. You're probably all more familiar with Riemannian geometry, and then famously there is the Riemann curvature, which is an invariant of the Riemannian structure. And it's a local invariant. You cannot, if you have a curvature at some point, you cannot like spirit it out by choosing different coordinates or choosing a different kind of chart. But here you can. So there is nothing like curvature. There is always those Darboux charts at any point. So from this perspective, it also, depending on interpretation, one can say that it shows that the symplectic geometry is a little bit like dull or empty, right? Because like locally, nothing is going on. Right. Okay, so why is it true? So how to prove the Darboux theorem? So in fact, my strategy will be as follows. You see, we are asked to construct V, U, and phi. And I'll start with some objects that I call V, U, and phi. And then I will change their definition to arrive at the good ones. So I first start with V, U, and phi, which are kind of the bad ones. But then I will kind of try to improve them. So in any event, let's choose a chart near our point M. So what does it mean, a chart? Right, I map a piece of a vector space. We know that it has to be of even dimension into M. So here is sitting our point M. Here is sitting 0. And I can always arrange it such that 0 is mapped to M. So here is my manifold M. Here is the point M. Here will be this open subset U, the neighborhood of M, and here I have R to N. So this is U, this is V, this is 0, and so that's this map phi, right? That's how we think about smooth manifolds. So smooth manifolds are covered by charts, and this is one of those charts. And I assume that 0 is mapped to M, so my chart is centered at the point M. Of course, a priori, this is not at all a symplectomorphism, but let me do the following. Let me negotiate this space to be the tangent space of M at M. And here I will also then negotiate the differential at 0 to be identity. So this is a little bit tautological. If I'm just thinking about this space, this chart sitting in the tangent space, then I can always just by definition say that this differential at 0 is identity. Right. Okay. So now, in fact, both these spaces are symplectic. So there are two symplectic forms on V. So the first one is just the constant symplectic form omega M. And the second one is the pullback. Do you mind if I slightly change notation? Yeah, let me call this guy F. Sorry. All right. And the second one is a pullback of the original two form omega under this map of the chart. So these are two symplectic forms, right? F is a diffeomorphism, so F star of omega is a symplectic form. And now I construct a family of symplectic forms. Let me denote it omega of t, which is equal to 1 minus t omega m plus t phi star omega for t between 0 and 1. Well, I said it's a family of symplectic forms, but it is not quite true, right? It is clear that d omega of t is equal to 0 for all t. This is obvious because these are two closed forms. However, the fact whether it is non-degenerate or not, it is not entirely obvious. Now, notice, however, that the pullback of omega to the point 0, right? It's a pullback from the point from the tangent space TMM, and the differential of this map at this point is just identity, right? So these two forms, they are probably very different on the rest of V. But at this very point, they're just the same. We just arranged our construction tautologically such that they coincide. So note that omega m is just equal to phi star omega computed at 0. Or this one we can also restrict to 0 because it doesn't matter so much. It's right. So this means that omega t at the point 0, right? It's actually independent of t because in this combination omega m is equal to that guy, so it is just equal to omega m. And it is symplectic, so it's not non-degenerate. It is non-degenerate. So it is non-degenerate at this point, and non-degeneracy is an open condition. Right? So this means that there will be some neighborhood, maybe smaller than V, such that this guy is still non-degenerate. V star, possibly smaller than V, such that omega t is non-degenerate on V for all t in 0, 1. So here there is this kind of smaller neighborhood. Very well. Now we can start using the Moser lemma. So on V prime, we have a family of symplectic structures. So right, and so we can define the Moser vector field for alpha t, for instance, given by the Poincare lemma homotopy. I think you discussed it, right, in the introductory lectures of so d omega t over dt. So V prime is sitting in TMM, which is a vector space. So this means that the Poincare homotopy is well defined just by scaling all the vectors back to the origin. So we simply define the primitive alpha t of d omega t over dt by this formula. Here, of course, the derivative will be just f star of omega minus omega m. Right? And then we define this family of Moser vector fields. Now, would they integrate? Difficult to say, right? So V prime is an open subset. It's non-compact. Maybe they wouldn't integrate. However, let's notice that if we choose some closed ball, which is compact in V prime, then it will integrate, but maybe it will start bringing you out of this ball somewhere, right? So let's formulate it in the following way, and let me see whether you agree with me. So there is some V double prime inside V prime, such that Vt integrates to a family phi t with phi 0 equal to identity of v double prime, and such that phi t of v double prime is always in v prime for all t from 0 to 1. So in other words, I choose, if needed, this v prime small enough such that the flow will be well defined and that it doesn't bring you too far away. So maybe here you can imagine, right? So I'm taking this v double prime here inside, really small, and then my phi t, it is bringing it somewhere, but not too far away. So I don't want to make a detailed argument, but you can imagine what I would do. I would first restrict to some compact ball. I would estimate the maximum of the norm of the corresponding vector field, and then I would make this v double prime small enough such that kind of with this estimate, my flow could not bring it to the boundary of v prime. I think, okay, let's discuss it. In fact, we'll talk about alpha t equal to 0 at 0, but even if not. To be honest, I don't see much of a problem, right? So, assume alpha t is not equal to 0. So, of course, very bad, right? I just need to make it very, very small, right? Or is it wrong? Okay, maybe he's right. Yeah, then I agree. Maybe I cannot bring it to t equal to 1, right? Because I want to bring it to t equal to 1. So, so let me make an extra remark. So this alpha t at 0, constructed by the Poincare homotopy, is actually equal to 0, right? Because that's the point to where we contract things. And this implies that Vt at the point 0 is equal to 0. Right. Probably you're right. That we want to use as well. So that so this means that I can always find a ball sufficiently small such that the norm of Vt is bounded by what I want. And this means that even for t equal 1 flow, I can be sure that this ball will not escape. Would you buy this argument? Kind of, I'm happy of your approval. What about the other people? Right. Yeah, I think that's a good point. This is right. So since Vt 0 is equal to 0, this means that the norm of Vt small near 0 and for t equal 0, 1, phi t of v double prime small enough does not escape v prime. Right. Okay. Very good. Now let's write let's write the resulting formula. So the Moser lemma tells us that phi 1 in general, phi t star of omega of t is equal to omega of 0. And in particular, t equal 1 story is phi 1 star of omega of 1, but omega of 1 is f star omega, right? Is equal to omega of 0, which is equal to omega m. Now finally for the Derboux theorem, put our V equal to V double prime, put our U to be F composed with phi 1 of V double prime in M, and put F to be equal to F composed with phi 1. Sorry, I kind of probably what I'm writing does not make much sense, but maybe better say replace V with V double prime, U with its image, and that's the correct map. Right? So I started with some map F, which was just some map defined in the chart. Now it was a wrong map. Now if I correct it with phi 1, so phi 1 is a diffeomorphism which acts here, and then after that map it with F over there. Right. So note also that here, because of this condition, because Vt of 0 is equal to 0, we know that phi 1 of 0 is equal to 0, and this means that F phi 1 of 0 is equal to M. So the new chart will also be centered at M as the old one. In fact, we'll see even hopefully today, we'll see more arguments which more or less repeat this structure. So let me give you two more applications of the Moser trick. One of them is very easy. The other one is maybe not so easy, but maybe we don't go over it in such a detailed fashion. So one more application. Let's say theorem due to Banyaga. It says the following. Suppose that N is a complex manifold and it has two Keller structures. Let's say a compact, complex manifold, and it has two Keller structures. And assume that Again, sorry for notation. Maybe I should denote them H0 and H1 as before, just to synchronize notation. And assume that the chemology classes of the corresponding symplectic forms coincide. So then, so there is a symplectomorphism. Yeah, I don't know whether I should call it M or N now, but okay, let's say a diffeomorphism of N, but viewed as a real manifold, such that phi star omega 1 is equal to omega 0. Now you see it kind of, it's a very, very strong statement. So it basically tells you that for two Keller structures on the same compact manifold, you only need to compare the chemology classes. You don't need to do anything else. So, so why is it the case? So it's a combination of the Moser lemma and one more consideration. So what's the consideration? So let's introduce a family of so let's introduce an interpolation between the two Hermitian structures that we have now. So we take 1 minus t times h0 plus t times h1, and we assume that t is between 0 and 1. So both 1 minus t and t are non-negative. So then, this is again a Hermitian structure, right? So you take a convex combination of two Hermitian products, you get a Hermitian product, right? You have all the kind of bilinearity features, and the positivity is still there, right? And non-degeneracy is still there. So is a family of Hermitian structures. So this means that if we define omega t, which is the imaginary part of ht, and which is, of course, given by the same formula. So these are symplectic structures for all T again. Because right, so that's this magic of the Keller story. Once you have Hermitian story, then it's automatically non-degenerate. Now closedness is clear because it's a linear combination of closed forms. Right? Now we simply use Moser. So what were the assumptions for Moser? Like kind of the existence of alpha t for compact manifolds, right? That's no problem. You just take whatever, any reasonable homotopy. Now the integration, if it is compact, then the integration assumption is okay. So the assumptions are verified for compact manifolds. So now Moser gives you phi t with phi 0 equal to identity, such that phi t star omega t is omega 0. So then phi 1 star omega 1 is equal to omega 0. Now let me do the following. Let me finish today by introducing one more definition, and then I'll give you one more application of the Ulema as a homework. So today I decided not to finalize the problem set before the class, and now kind of since we came here, kind of I will redo a little bit the problem set that we'll have it available tonight, I think, on the Camilla. Or do we already have? Okay, yeah, let's make it available tonight. So so let me talk about submanifolds of symplectic manifolds. So recall that for vector spaces, we had some kind of, not a classification, but we had many denominations of different subspaces in a symplectic vector space. So let me give the following definition. Let's assume that M omega is symplectic, and X in M is a submanifold. So then one says that X is, and well, what were the denominations that we had? Isotropic, coisotropic, Lagrangian, symplectic. If Tx x inside Tx M omega x is isotropic or coisotropic or Lagrangian or symplectic. For all x and x. Perhaps just some simple remarks about it. Maybe the remark number one, if x in M omega is symplectic, so this means what? This means that Tx x intersection with Tx x omega is equal to 0 for all x in x. And we'll have an exercise saying that if this is the case, then omega x restricted to the tangent space Txx is actually non-degenerate, right? So this is, you have a two form on the big space, you restrict it to the small space, and this condition exactly means that this restriction is actually non-degenerate. So what does it mean? So as before, let's introduce the map I, which embeds x into M. This is just a tautological map, kind of sending the point of x to itself. Right? So then, what is I star of omega at the point x? Well, this is exactly this object. This is omega x restricted to txx. So this means that the restriction of the two-form of M to x is a non-degenerate two-form. Right? And of course, its Theorem differential is 0 because the Theorem differential of omega is 0. So this means that x together with omega restricted to x is again symplectic. So this is, of course, a little bit of a kind of problem with our it sounds a little bit tautological, but we define symplectic submanifolds as submanifolds where the tangent subspace is a symplectic subspace. But it turns out that they're actually symplectic in the sense of a symplectic manifold, with the two-form being the restriction of the two-form from M. Right? So one example of it we already saw today in the Keller case. Right? Complex submanifolds of Keller manifolds are Keller manifolds and, as a consequence, symplectic manifolds. Maybe the last remark for today. Suppose that x suppose that x in M omega is coisotropic. So, right, what does it mean? This means that txx omega is contained in txx for all x in x. So how can one imagine it? So here there is a kind of relatively interesting and complicated picture. So this is our M. Now inside M somewhere there is this x. So you imagine a tangent space, so txm. Here inside is sitting the tangent space txx, and somewhere inside it is sitting one more subspace txx omega. So in fact, for us, it will be like in the kind of also in the study of group actions. So this will be an important situation. So there will be like this triple of subspaces: the big tangent space, the smaller tangent space, and inside there is one more subspace. In fact, it's related to the behavior of the form omega, right? We can still define as before I star of omega. So this is a two form on X. It is clear that it is a closed form, but in general, it is degenerate. So kind of that's one of the questions maybe for the next problem set, and also for us to discuss next time kind of how this degeneracy of the form on quasi-tropic submanifolds look like. So, so let me stop here. So we'll continue this discussion next time, and also you will see some of these things in the problem set.